Welcome to our lecture online, and here's an interesting example of how you apply the physics related to RCL circuits to come up with the reactance and the impedance and a whole bunch of other things regarding one of these types of circuits. So let me explain. We have a voltage varying power source. We have an RMS voltage of 120 volts, but there's a cycle where the angular, let me start over again because I'm making no sense at all. All right. Welcome to our lecture online, and here's a really interesting example of how you work with RCL circuits. So RCL circuits are circuits that have a varying voltage source. It varies according to a certain frequency. This is the radial frequency. We have an inductor, we have a resistor, and we have a capacitor, all in series in the same circuit. And inductors are devices which oppose a current change, which means that the voltage drop across the inductor happens before the voltage drop across the resistor. They're out of phase by 90 degrees. And the capacitor is a device such that first fills up with charge, and then the voltage difference builds up as charge builds up across the capacitor. So the voltage across the capacitor is out of phase with the resistor by 90 degrees, and it turns out it lags the voltage across the resistor by 90 degrees. All right, so we have a whole bunch of questions here. You're supposed to find the inductive reactance, the capacitor reactance, the total reactance, the impedance, the phase angle, the current through the circuit, the IRMS through the circuit, the power consumed by the resistor, and then at the end here, I want you to find V sub r divided by the cosine of that phase angle to see what that is equal to, and it probably will be a surprising result. So let's just go through the mechanics how to do that. This is a very mechanical type problem where you follow each step one step of the way and see what you get. You also need to draw a phasor diagram, which I'll show you how to do in just a moment. So let's start with part A. We're supposed to find the inductive reactance, and by definition the inductive reactance is equal to omega times L, and omega is equal to 2 pi times the frequency. So you can also write this as 2 pi f, which is equal to omega times the inductance L. Now, to find the f, we can then say, well, that means that f is equal to omega divided by 2 pi, and omega is 377 hertz, and 2 times pi, let's see, what does that equal to? So let's take 377 and divide it by 2 and divide it by pi, and you get 60 hertz. Okay, so that would be the cycle frequency of the voltage. So the voltage is varying according to what we see here, 60 times per second, 60 cycles per second. You can also say that's equal to an angular frequency of 377 hertz. All right, so let's use omega sub L. So this is equal to 377 times, let me write the units in. It's always a good idea. So that would be hertz times the inductor value, which is 0.5 henries. And it turns out, when you calculate that, so 377 times 0.5, we get 188.5, and that would be ohms. The reactance is just like the resistance, the units are ohms. Doing the same for the part B, which is the capacitive reactance, that is equal to 1 over omega times C, so it's equal to 1 over 377 hertz, and the capacitance, what's 6 microfarads, which is 6 times 10 to the minus 6 farads. So what is that equal to? So let's find out in just a moment. 377 times 6e to the 6 minus equals, and take the inverse of that, and we get 442.1 ohms. All right, so what you can see here is that the capacitor is more of an impedance, or more of an opposition to the current flow than the inductor here. So therefore it has a greater reactance than the inductor, so the whole circuit will act more like a capacitive circuit. So that means that the voltage will lag the current. All right. The third part is we're supposed to find the total reactance. Now, before we do that, I'm going to draw a phasor diagram. So we're going to draw the x sub L in the upward direction, because the voltage across the inductor leads the voltage across the resistor. Then we have the resistance here, and then we have the capacitor reactance here. So x sub C, this is R, this is x sub L. And so notice that the length of the vectors are approximately proportional to the value of the reactances and the resistance. So here we can say that X sub L, and let me write it in a slightly different place. Okay, so you can see that X sub L is equal to 188.5 ohms. We know that the X sub C was equal to 442.1 ohms, and the resistance was equal to 200 ohms. So here's my phasor diagram indicating the reactances and the resistance. Now to find the total reactance, we're going to add these two together, but notice they're like vector quantities, they're pointing in the opposite direction. So to find the total reactance X, that is equal to the difference between the two reactances, so that would be the X sub C minus the X sub L. So in this case, that would be 442.1 ohms minus the 188.5 ohms. Oop, that's not a very good ohm symbol right there. So 442.1 minus 188.5, and we get 253.6 ohms. This is equal to 253.6 ohms. That's the reactance. And notice what we do here when we add these two components together. You will end up with a net reactance right here, X, which is equal to the difference between these two, so X sub C minus X sub L, and that in this case that would be equal to 253.6 ohms. All right. At this point, we're ready to go ahead and calculate the impedance. The impedance would be the vector sum of the resistance and the reactance. And notice if we add these up vectorially, you'll end up with something that looks like this. And this here represents the impedance of the circuit. And then also the angle between the resistance and the impedance is called the phase angle. Okay, to find the impedance, you can see that then becomes kind of like calculating Pythagorean theorem. We have the impedance, Z is equal to the square root of the reactance squared plus the resistance squared. So this is equal to the square root of the reactance was 253.6 ohms. We have to square that, and then we add to that the 200 ohms of the resistance, and we have to square that as well. And let's see what we get. So we have 253.6, we square that, plus 200, we square that as well, add them together, take the square root, and we get 323 ohms. And that is the total impedance of the circuit. So the total opposition to current flow from the circuit can be found by finding the impedance. In this case, is 323 ohms. Okay, the next part, E, we want to find the phase angle. The phase angle is this angle here that shows how the voltage here lags the current by an angle phi. And so we can find that by taking the arctangent of the opposite side, which is the reactance, divided by the adjacent side, which is the resistance. And so this is equal to the arctangent of X, which we said was 253.6 ohms, divided by the resistance of 200 ohms. And what do we get there? 253.6 divided by 200, and take the arctangent of that, and we get 51.7 degrees. All right, so that's the phase angle. Now, next, we're supposed to find IRMS, the root mean square current of the circuit, which is determined by the voltage RMS of the power supply and the total impedance. So using Ohm's law, IRMS is equal to VRMS, the voltage that provides the current flow, divided by the total impedance of the circuit, Z. So in this case, that is equal to 120 volts RMS divided by the impedance of 323 ohms. And so that means that in this circuit, we have a current of 0.3715 amps. I keep a few extra significant figures so I don't get a rounding error. Okay, next, we want to find the power consumed by the resistor. So G, the power consumed, is equal to I square R, and of course in this case it will be IRMS squared times R, the I that we just found. So this is equal to 0.3715 amps. We square that and we multiply times the resistance of 200 ohms. So we square that amount, and then we multiply that times 200, and we get a power consumption of 27.6 watts. All right, that's a hefty consumption for a resistor. Do not touch that after a while because that resistor will get pretty hot. Okay, now we have one more thing to do. Let's say I didn't add that, but what I'm going to ask you to do also is I want you to find the voltage drop across the resistor, I want you to find the voltage drop across the inductor, and the voltage drop across the capacitor. Let's do that first before we answer part H. So, the voltage drop across any device is the current through the circuit times the resistance. Now, of course, in the case of the inductor and the capacitor, that will be the reactance. So, the voltage across the resistor is equal to I RMS times the resistance. And if we do that, we get the following. We get a 0.3715 amps, and we have to multiply that times the resistance of 200 ohms. And what do we get? So 0.3715 times 200, and we get a voltage drop of 74.3 volts. Then next we're going to find the voltage across the inductor, which is the IRMS, times the reactance, inductive reactance, X sub L. So that will be 0.3715 amps, and multiply that times X sub L, and X sub L was 188.5 ohms. So we get 0.3715 times 188.5, and we get 70.0 volts. And finally, the voltage across the capacitor is IRMS times X sub C. Now, of course, that's not the constant voltage across each of the devices because that will change because it's a voltage varying circuit. The voltage across these devices will change. This would be like what we would consider the maximum voltage at any point in time during the cycle. So we take 0.3715 amps times the reactance, which was 442.1 ohms. Let's do that. So we get 0.3715 times 442.1, and we get 164.2 volts. 164.2 volts. So that would be the maximum voltage drop across each of those three devices. Notice that when you add those three together, you do not get 120 volts here, which makes sense because the voltage drops across these three devices occur at different times in the cycle. And so they're out of phase. So now I asked you to also calculate V sub r divided by the cosine of that phase angle. So let's do that. So for part H, you're supposed to find V across the resistor divided by the cosine of the phase angle. And let's see what we get. So the voltage across the resistor is 74.3 volts, and we divide that by the cosine of the angle of 51.7 degrees. And let's see what we get there. All right, so 74.3 divided by 51.7, take the cosine of that, and that equals, and guess what? 120 volts. So to see if you did your problems correctly, in the very end, if you take the voltage drop across the resistor and you divide it by the cosine of the phase angle, you should get back the RMS voltage from the voltage source. And if you do that and you get that same number, then you did the problem correctly. Okay, and that's a good representation of the voltage drop across the whole circuit. All right, it was a complicated problem, but if you do the problem in a very specific way, in that particular order, it's not too bad. All right, give it a try. Good luck.